All right. So let's start this problem. So what we have here, again, we want to find the equation for slope and displacement for this structure. Now what's different from the problems we've worked before, you'll notice, is that the load is discontinuous. In that we got no load and then suddenly a point load, a singular load, which always kind of messes the whole thing up. And then we have no load again. So you might recall that if I try to write a moment equation for this structure, I can't write one for the whole beam. I'm going to have to write one that's good from 0 to L over 2, and then a second one from L over 2 to L. Now they're not going to be very complicated, but I'm going to have to break it up. So let's start with that. So what I'm going to do first is I'm going to cut the structure somewhere between 0 and L, and I'm probably going to work the left-hand side. So I'm going to look at this little segment here of length X. Then when I cut it over here, I'm deciding whether to work the left side or the right side. I like the right side. It looks pretty simple. And in that case, this little segment here that I'll be looking at will be L minus X. So I'm going to find the moment based upon those two pieces. In both cases, you see, I'm going to need my reactions. So before I get started, I'm going to need to know the reaction at both A and B. So let's do that first. So I'll come over here quickly, and we'll sum moments to find my reaction. I'll sum moments at A just to get started. So there's my equilibrium expression. So summing moments at A, my applied load P creates what kind of moment? Positive or negative with right-hand rule? Negative. So it'll be P times the distance from A to the load, L over 2. And then I'll have my reaction By. What kind of moment does that create about A? Positive. The force will be By, the length will be L. And it's really probably no big surprise that when you solve for By, you get P over 2. Again, I don't think it should be surprising. You have a simple supported B, a load P right in the middle. You're probably going to expect that both AY and BY carry equal load for half. And I found that to be true with BY. And pretty easy just to quickly sum forces in the Y direction and find AY. So both AY and BY are acting up. I assume those are positive. And then, of course, P is acting down. I assume that was negative. So now when you solve for AY, you also get P over 2. So I'm going to start with this left-hand section. I'm going to draw a little free body diagram of distance X. And of course, we're looking for the moment here. That's the positive bending moment. And our reaction there is P over 2. So if I sum moments at the cut that I just made and make sure that's in equilibrium, what do I get? Well, there's my moment. It's the same as my sign, so that's positive. And the P over 2 force is creating negative moments. So that'll be P over 2 times X. So my moment for this first segment is just going to be Px over 2. Now in the first segment, I only can check one thing about my moment. I know that the moment at A is 0, and that would be at x equals 0. And if I put in x equals 0 here, I do get a moment of 0. I can't use this equation to predict the moment at B, right? Because this is only going to be valid from where? From 0 to L over 2. So that means I need to go from L over 2 to L. And that's this side. So in that case, I have a little free body that looks like this. Remember, we're working the right-hand side, so I've got my B, which again is P over 2. I'm going to have my positive bending moment at the cut. And this little distance is going to be L minus X. So if I sum moments here, using right-hand rule, at the cut, what do I get? Well, with right-hand rule, this moment is negative. And about the cut, the P over 2 force creates positive. So there's the force, P over 2, and the distance is L minus X. So it looks like my moment is going to be P over 2, L minus X. I can check that too. Where do I know the moment somewhere between L over 2 and L? At B, right? When X is equal to L, and when you put in X equal to L, again the moment works. Now that I have two moment expressions, can I do another check? Well, these equations share one point in common. Where? L over 2. So if I put an L over 2 here, what do I get? I get PL over 4. And if I put L over 2 here, what do I get? I get PL over 4, so they match. So I feel pretty good that my moment expressions are correct. So I'm going to kind of draw a little break right down the middle. And because this is really section 1, and this is really section 2. In fact, I'm going to come back and call this the moment at section 1 and the moment at section 2. And I'm going to integrate this moment twice to get a displacement equation in section 1. And I'm going to integrate this moment twice to get a displacement equation in section 2. So let's do that. So we'll start off with the slope in section 1 is the integral of M1 over EI. Well, I got a P over 2 in common, so I'll factor that out, P over 2 EI. And I just have the integral of X dx, which is pretty easy. That's P over 2 EI X squared over 2 plus my first integration constant. Do I know anything about the slope in section 1? Well, not from this support, right? We do know the displacement at A is 0, and we know the displacement at B is 0. Right now, it doesn't seem like we know anything about the slope, so let's just leave it there and integrate that one more time. So the displacement in equation 1 is going to be the slope. Integrate the slope. So I'm going to integrate that equation. So I'll get P over 2 EI times X cubed over 6 plus C1X, and now a new integration constant. We can probably solve that one for something, right? I know the displacement of X equals 0. I can put in X equals 0 here. This goes away. This goes away. It looks like I can get C2. But let's just hold on for that. So let's go back now to the right-hand side and do that same process for section 2. So the slope in 2 is the integral of the moment in 2 divided by EI. So again, I've got a common factor of P over 2. So I'll factor that out. And then I'll integrate that. I'll have Lx minus x squared over 2 plus another integration constant. I'll call that C3. And I don't know anything about the slope in section 2 right yet. I don't know for sure. It's not definitely, I don't know the slope is 0 at D. So I'll leave that alone and I'll integrate it one more time. So I now get the displacement at 2 is the integral of the slope at 2. And what do I get? Well, there's my constant, P over 2EI. And let's see, that's going to be Lx squared over 2 minus L cubed over 6. Integrate C3, I get C3x, and then another integration constant, C4. So now I got 4 unknowns, C1, C2, C3, C4. How am I going to solve for all those? It seems I only have 2 conditions that I know for sure. But there are actually others, right? So let's write down what they would be. So I know, I'm going to come back now. Let me at least circle these so you can see them. There's C1, C2, C3, C4. The only one that I can see right off the bat that gives you a solution is what? When x is equal to 0, the displacement is 0, right? And I'll put a number there. That's like number 1. So plug in x equals 0 here, 0, 0. The only thing I get is C2. So, hey, it's not so bad. I got one of my constants. I also know that if I come over here and do, say, condition 2, this is once I already know. I know in this case that at x equal L, my displacement is 0. So I got to put in x equal L here. So I have L cubed over 2 minus L cubed over 6. So that's 3 6 minus a 6 is 2 6. Looks like the 2's cancel, right? And I should get what? P L cubed over EI. Is that what that whole term turns to at x equal L? I think it does. You guys with me on that? And then plus C3L plus C4. Oops, 1 equation, 2 unknowns. Can't solve that. So what do? It seems I've run out of conditions.
Can't you just find C4 and plug in C4?
How do I find C4?
C4 is equal to negative PL over 3 PI minus C3L. And then just plug that in.
Well, I only have 2 equations, and I have 4 unknowns. I don't think you can solve that, can you? So I need 2 more equations. What? See? So you're kind of thinking, what? How can I solve for C1?
What is that angle? So you come to the middle.
Well, let's talk about it mathematically. I have 4 unknowns. I've written 2 equations. There is no way to solve for 4 unknowns with 2 equations. Is there? I hope you say no, definitively, because there is not. So I need how many more equations? 2. What 2 other conditions about this being can you think of physically that have to be true? Were you talking about angle? Okay, so I have an equation for the slope in region 1, and I have an equation for the slope in region 2. Did they share a point? At L over 2. So it's possible that my third condition would be what? The slope in 1 at L over 2 has to equal the slope in 2 at L over 2. There's a third equation. What else is true? If the slopes have to match, wouldn't the deflections have to match too? I think they would. So a fourth equation would be that the displacement in one where they match at L over 2 has to equal the displacement in the second one at L over 2. Now before we go down that road, let's just take a look at this, shall we? Theta 1 evaluated at L over 2. Here's theta 1 evaluated at L over 2. Gives me an equation. This is C1. So I'll have C1 on this side. What will I have on the right-hand side? I'll have C3. Can I solve for one of those with that equation? No. What about this one? So now I have an equation in C1. That's on the right-hand side. And what's going to be on the left-hand side? C3 and C4. That's one equation and 3 unknowns. Can I solve for that one? No. So that means you'd have to solve equation 2, 3, and 4 simultaneously. That is beyond the scope of this class on an exam. If you're sitting at home and you Mr. Hernandez, yes. If you're sitting at home with lots of resources, then yeah, do it. Can imagine if I put another point load in here, like right there. Now what happens? I have to write 1, 2, 3 sets of equations. And each set generates 2 unknowns. That's 6 unknowns. So I'd match them where they shared here, 1 and 2, and I'd match them where they'd share here, 2 and 3. You probably have 5 equations and 5 unknowns. You can see this process will continue that way. So it'll work. It does work. But it does take some very tedious and takes very complicated. So this is where this tool kind of runs out of gas. It will, in the analogy, it will drive the screw into the piece of wood, but this is like the sledgehammer approach. It's not the elegant approach. It will work every time. This is your sledgehammer approach. But if I gave you this problem on the exam, this would not be the proper way to solve that problem. I'll show you in a minute how to solve this problem much simpler with a different technique. Now, if there is a shorter cut solution to this, and it's to notice that since the load is right in the middle, then where do you think the slope of the beam is 0? Right in the middle. So when I evaluate this slope at L over 2 and this one at L over 2, they're not equal. They're equal to 0. So if I go back and look at theta 1 is in terms of only one unknown C. I can solve for that. You plug in L over 2 here, you'll get a value for C1. It's not 0, but you'll get a value. One equation, one unknown. Same thing with theta 2. You'll come over here. You'll set this equal to 0 at L over 2. You'll get C3. But that only works for what? This one particular problem. I move this load anywhere left or right, and that doesn't work, and you're back to this. This works every time, but it's much more complicated. Okay? So, advantages, disadvantages. All right? A problem like this, which we just worked, direct integration has tremendous advantages, right? You can write one equation for the moment, you get everything you need for the whole beam everywhere. Big advantage. The disadvantage comes when the moments are discontinuous, and you have to write multiple moment equations, and you have to write multiple displacement equations, and then you run into the problem of matching your edges, and that can be very problematic for your solution. Okay? So we'll stop with that.